Hello everyone, thank you for tuning into my video. Today I will be discussing stacks and queues. So what is a stack? So a stack is a last in, first out data structure. So what does this mean? You can think of a stack as like a stack of objects like books on a table. So the first book that or the last book that you put on top of the stack of books is the first book that you remove from the stack of books. So a stack data structure has two operations. You can push an element onto the stack, and then you can pop an element off of the stack. So a queue, on the other hand, is a first in, first out data structure. An analogy to this is waiting in line in real life. So the first element in is the first element out. Uh, queues have two operations. In queue, you can in queue an element into the tail end of the queue, and you can dequeue an element from the front of the queue. Queues are described by their tail end and their front end. We can implement stacks and queues using linked lists. In this way, push, pop, in-queue, and dequeue are of constant time complexity. Time complexity. So let's implement a stack. So we can implement a stack by defining the head node and the number of elements. So we want to keep track of the number of elements. Similarly, the queue is defined by its head and its tail. And we also keep track of the number of elements in a queue. So to add elements to the queue, we need to define nodes that are serve as elements of the queue or the stack. So how do we define the pop method and the push method for a stack? So pushing an element to the top of the stack is similar to adding a head, is analogous to adding a prepending a head node to the head to the linked list. So what we can do is we can define a function is empty. which returns if the stack has elements, already has elements. Or actually, take that back. This returns if the stack does not have elements. We can also define size, which returns the number of elements. We can take these and define the same two functions for Q. So when we push a element onto a stack, we check if the stack has elements. So the head becomes the new node. So we can define the new node. So let's test this out. So we create a stack. Let's see if we can push a value into the stack. Value is not defined. Okay, yeah, so we didn't need to pass in a value to the push method. And we can see that the value of 1 is pushed into the stack. So we can write a function that prints out the stack in an array. So let me do that real quick. To array. Return output. Okay, so now What if the stack is not empty? We need to set the pointer of the new node to the head, and then we need to update the head to be the new node. Let's try adding a stack, adding another element to the stack. We have to add one to the number of elements. Let's see. It looks like the new node is becoming the head. Maybe this needs to go in else. And this number of element needs to go outside. Because when we had the empty list, we weren't updating that number of elements. So let's see. So that should work. So now to create a pop method, so if the stack is empty, we return nothing. Now to remove the element from the top of the queue, we want to save the element that's popped, and then we want to update the pointer so that the next element in the stack is the new element that's on the top of the stack. So let's create a variable value. And then once we save that value, we can update the head. So this effectively removes the node from the linked list. So we save the value of the head, we update the head to be the next value, and then we decrement the number of elements, and then we return the value. Let's console log this as well. We are removing 2, but let's see. Yeah, I guess that's right. Let's see. Node. Oh, let's just do value is equal to head dot value. So now we'll return the value that we pop. So that concludes this video. In the next video, I will discuss how to implement a queue.